G'day guys, complex numbers and introduction. Quite a lot of things to get through in one take, so hopefully I don't have to reshoot this. Complex numbers. Okay, I think the first time that you probably get an understanding or hear about non-real numbers is when you're trying to solve something of the form x squared plus x plus 1 equals 0. So if you were to solve this, obviously you can't factorize, you would have to go and use the quadratic formula. X is negative b plus or minus b squared minus 4ac, all square rooted over 2a. So x would be negative 1 plus or minus b squared, so 1 squared minus 4 times a times c, so times 1 times 1. And that's all square rooted, and this is all over 2a, so all over 2 times 1. So this would come all the way down to being negative 1 plus or minus the square root of negative 3 all over 2. Now it's the square root of negative 3 that you're probably kind of accustomed to, and you would just say, well, there are no real roots. This parabola, if you will, is floating. So it's not crossing the x-axis. There's no real roots. However, we have been lying to you. There are roots, they're just imaginary. So someone asked back in the day, how would you solve x squared equals negative 1? You'd obviously square root both sides of the equation. But what does that mean? It means that we need a new number system. Now, I'm going to write the number system vertically. So, someone came up with, obviously you can still have 0 in these numbers, because 0 is neither positive or negative. We won't really get into that. But what they determined, I can't remember the history exactly, but that the square root of negative 1, they said it was imaginary. I'll actually write that word, imaginary. So they said the square root of negative 1, they said was imaginary. So they came up with a number system of imaginary numbers, and we're going to write it vertically. So let's have a look. They went positive i's upwards, negative i's downwards. So if we were to do something like, what is the square root of negative 4? Well, we know from surds and from the product of square rooting that we could say that that is 4, square root of 4 times the square root of negative 1, which is just 2. And we know that the square root of negative 1 is now defined as I. So that would be 2i. That would be sitting there on the number line. What about negative square root of negative 9? That's a bit hard to see, but that would be negative square root of 9 square root of negative 1, which would be negative 3i. Negative 3i. And obviously all i's in between, so if you wanted to say take square root of negative 7, then that would be some kind of irrational number of I somewhere in there. So that is what the imaginary numbers are good for. So we can now square root and express those values on this new system of imaginary numbers. So now we've got two number lines. We have the real number line, which I'll express going horizontally. So these are the real numbers. And we have this new vertical number line. And we express these are the imaginary numbers, IN. Now the real numbers go up as we normally do, 1, 2, 3, or negative 1, negative 2, negative 3. But now we can count going up a number of i's. So I, 2i, 3i, negative I, negative 2i, negative 3i. Right, we now have a two-dimensional set of numbers. Interesting. So we can express a number kind of like vectors, and this is where I'm going to introduce to you a little bit of vector algebra, if you will. So we could say that Z, we usually use Z or sometimes W for complex numbers. So just side note, imaginary numbers are just on this vertical line. These are imaginary, these are real. Complex numbers are a mixture of both. So if we were to say Z is 1 plus 2i, it would be kind of like graphing linear equations. It would be 1 plus 2i. It would be the number floating there. That's 1 plus 2i. If we had Z, I believe I've gone off the page. Z equals 1 plus 2i. If we had Z equals, I don't know, negative 2 minus 3i, that'd be negative 2 minus 3i. It would be down there. Negative 2 minus 3i. So these numbers, there could be numbers anywhere in this plane, and that is called the, it's getting messy, the complex plane. That is the complex plane. So we'll just make another note here. So complex numbers, Z is A plus BI, they're made of two parts, a real part and an imaginary part. They're kind of like they're just like vectors. I'll show you what I mean in a second. So how do operations in a complex plane work? So obviously 2 plus 3 is 5, and that works on the number line. So on the number line you have, going from 0, you've got the vector 2 and you've got the vector 3, and when you take that vector 3 and you add it to 2, it takes you all the way out to 5. And that's how it works in the complex plane as well. So addition. It's going to be quite simple, but we're going to go A plus BI, and we're going to add C plus DI. Well, addition just works quite simply. A plus C plus, and we're going to take the B, we're going to take the imaginary parts and just add those together. B plus D I. So just add your real parts and add your imaginary parts. Subtraction. So subtraction is very similar, mate. It's C plus DI. When we subtract your real and subtract your imaginary part. I'm just going to take a quick side step here, and I'm just going to explain what this means geometrically in terms of kind of vectors. So I've got two complex numbers here. I've got Z1 is 7 plus 5i, so it's 7 in the real, and it's 5 in the imaginary. And you can kind of think of these as vectors, right? So it's almost got, we usually just use dots, because if you were dealing with lots of complex numbers and you had lots of vectors drawn, it gets really messy. So they can be expressed too as a point in the complex plane or a vector, a distance from the origin. So obviously it has some distant direction and some magnitude, okay? And we're also going to have Z2 as 4 minus 8i, and I'm exaggerating the size of these dots as well just to make it easier to see in the video. So what does addition look like? Well, Z1 plus Z2 is the real parts added, so 11, and the imaginary parts added, minus 3i. So 11 minus 3i. That there is z1 plus z2. And it wouldn't matter the order as well. Now, have a think about why the order doesn't matter. This is how you add vectors. You take this vector and you're adding the magnitude of this one. So leave this vector where it is, we're just going to add this one to it. So hopefully you can see that when you add this vector on, you're going to have z1. Then you're going to, after you've travelled along z1, you're going to add z2. So just the direction and magnitude of z2. So that goes there. If you did it the other way around, you would have z2 and you would be adding z1. So you're going to take z1 and you're going to add z2 to it. So z1 and then you're going to add, z2, then you're going to add z1 and you're going to end up there. And that's, I think, the rule of parallelograms. So it doesn't matter which way you go. z1 plus z2 or z2 plus z1, you'd still end up at that spot. Obviously subtraction doesn't work that way. I'm just going to show you one subtraction. So one, we go z1 minus z2, z1 minus z2. So we're going to just go the real parts subtracted, 3, so 7 minus 4, and then 5 take away negative 8, so plus 13i. Now where does that sit? We'll do this one in green. 3 and 13i just goes off my grid actually. There we go. 3 plus 13i. Hopefully you can see that. You might want to go full screen for this video. So that is, I should have drawn the other line as well, but that is this vector here. That is that vector. And we had this vector over here as well, didn't we? So 3 plus 13i, that was z1. And now instead of adding z2 to it, instead of adding it on and going this way, we're going to be subtracting this off. So we're going to be going z1 minus z2. So that whole vector is going up there. And so we're going to be subtracting off z2. So that's that's a crude geometric interpretation of addition and subtraction. But that's how it works. That's how it's worked in one dimension. That's how it works in 2 dimensions. Okay, I'll do the geometric interpretation, multiplication and division a wee bit later on, because it makes more sense when we do that in polar form. Okay, now we'll do the algebra of multiplication though. So, multiplication of complex numbers. A plus bi multiplied by c plus di. Alright, just like quadratics, we have everything in the first bracket multiplied by the second, so a times c. Then we've got a times di. We've got bi times c, or bci. And then we've got bdi squared. We know that I squared is -1 though. So we have AC minus BD plus AD plus BC multiplied by I. So that is how the multiplication of complex numbers works. So maybe an exercise for you would be to confirm that -1 plus 3i times 2 minus 5i, just confirm that that is in fact 13 plus 11i. So it's pretty simple. You just got to remember I squared is -1. Next, division is our last operation that we need for complex numbers. How could we go about -1 plus 3i, 2 plus 5i? How would you actually do that division? Well, it's much like rationalizing the denominator. So what does that mean? We want to kind of get rid of the imaginary part in the bottom. And there's a special process. We multiply numerator and denominator by the complex conjugate. That's an important term actually, a complex conjugate. So what does that mean? The complex conjugate of the denominator, in fact. So we're going to have negative 1 plus 3i, 2 plus 5i, and we're going to multiply this by 1, but 1's just going to look like this. So it's just the opposite sign on the complex part. You're going to see why that's useful. So as we saw above, that's going to give us 13 plus 11i, and on the bottom we're going to get 2 squared plus 5 squared. Obviously the 2 lots of negative 5i are going to cancel with the 2 lots of positive 5i, and then you're just going to get 2 squared, and because we've got negative 5 times 5, but we've also got I squared, that gives us a positive 5 squared. So this actually becomes 13 over 29 plus 11 over 29i. We usually want these written as real parts and imaginary parts. We wouldn't like to write this as 13 plus 11i over 29. We usually like them split into real and imaginary. So what's the geometric interpretation of a conjugate? It's pretty simple. So if I just draw up a complex plane quickly, let's go on the line so it's nice and easy. We have our imaginary going in this direction, and our real going in this direction. If this is I, its conjugate is just negative I. It's just a negative real part. So that distance is the same. If we have z equals a plus bi, then its conjugate is going to be the same distance, just in this direction. And those lengths are going to be the same. And that's a minus bi. Now the symbol we use for conjugates is z hat. So that's the geometric interpretation of conjugates. They're symmetrical around the reals. It's just the opposite sign on the imaginary part. Okay. So that brings us to the properties of conjugates. Right, so the properties of conjugates are pretty simple. If we have 2 complex numbers, we add them and then take their conjugate. That's the same as taking their conjugate and then adding. That's nice and easy. If we have 2 complex numbers, we multiply them, then take the conjugate. That is the same as taking the conjugate of each and multiplying. If we have a complex number raised to the power of n and we take its conjugate, that is the same as taking its conjugate and then raising to the power of n. So they're pretty standard conjugate properties. The complex numbers seem pretty scary at first, but we realise pretty quickly that their operations are quite simple. The next thing that we want to look at is a modulus. And in a couple of days I'll do a video going through arguments in polar form. So if we have z equals a plus bi, a real part a and imaginary part b, then we're going to talk about the modulus. So I'll draw it as a vector and not a point on the complex plane. Imaginary, real. The modulus, and we use these vertical lines on each side of the z. Well, this just means length, size, or absolute value. Now the absolute value or length, well, it's obviously just from Pythagoras. real part squared plus imaginary part squared, all square rooted. So that's just by Pythagoras. If we wanted the length or the size of that vector, which is quite useful for physics, then we would use this form here, just the real part and imaginary part squared. That would give you the absolute value, also called the modulus, also called length, also called size. So a few different ways of thinking about that. Note, though, that z times its conjugate, so a plus bi, a minus bi, actually gives a squared plus b squared, which is obviously just the modulus all squared. So if you ever wanted to try and find the modulus, you can multiply by its conjugate, or vice versa. If you end up multiplying by a conjugate, you could just write that as modulus. And that kind of actually now I think about it, fulfills division. It fulfills that division rule that we just saw earlier, where we multiply by a conjugate. So if we had ZW, then we'd have Z conjugate of W over W conjugate of W. As we saw before, we had Z W conjugate over the modulus squared. So that's kind of actually what we saw before with the division. So that is kind of all the basic properties of complex numbers. So as a review, the first time we kind of come across imaginary numbers is when we have no real roots in quadratics and we're solving. We come up with this new number system, we do it vertically, and we define I as the square root of -1, because every negative number can just be written as a product of -1 times the real number, and so we can just scale all those numbers along this imaginary number line. Once we overlay the imaginary numbers and the real numbers, we come up with a complex plane. So complex numbers are part imaginary and part real. We then went through and we looked at complex numbers, real and imaginary parts. We looked at addition and subtraction as vector addition and subtraction. So hopefully vector addition and subtraction makes a little bit more sense on that now. And then we've also then just gone through the properties, the division, the multiplication and division properties as well. So complex conjugates are a pretty powerful tool. They have a bit of a geometric interpretation, which is really important when we do complex loci and complex geometry. But we'll come back to that in a couple of videos' time. And then we just looked at the conjugate properties. So the conjugate rules are pretty simple. Modulus is obviously quite intuitive. It's just a length of that vector. And that kind of fulfilled a bit of that division rule that we did before. Hopefully that makes sense. Like that smash button.